Look up at the night sky, and what do you see? A scattering of stars, maybe a planet or two familiar points of light that have guided humans for millennia. But here's the thing, what you're seeing is barely a fraction of what's actually out there. The universe is hiding secrets on a scale that's almost impossible to grasp. For every star visible to our eyes, there are countless others lurking in the shadows, stars so strange, so distant, or so elusive that we'll never lay eyes on them, yet we know they exist. Some are cloaked in cosmic dust, others swallowed by the unfathomable darkness of black holes, and some are simply too far away for even our most powerful telescopes to catch more than a whisper of their light. Today, we're diving into one of space's greatest mysteries, 30 hidden stars you'll never see but that shape the universe in ways we're only beginning to understand. These aren't just ordinary stars lost in the crowd, they're cosmic phantoms, each with a story that defies imagination. Take, for example, the stars trapped in the heart of galaxies so dense with dust and gas that not a single photon escapes to reach us. Or the ones orbiting so close to black holes that time itself slows down, stretching their light into an infinite red smear across the fabric of space. And then there are the stars born in the early universe, so ancient that their light has faded into nothingness, leaving behind only the faintest echoes in the data of astronomers. What makes these hidden stars so fascinating isn't just that they're invisible, it's what their existence tells us about the universe's grand puzzle. They challenge our understanding of physics, push the limits of what's possible, and remind us just how much we still have to discover. Over the course of this journey, we'll uncover their secrets, explore how scientists detect the undetectable, and piece together the clues that reveal these celestial ghosts. So buckle up, we're about to venture into the unseen, where the universe's most enigmatic stars hide in plain sight, waiting to be discovered not with our eyes but with our curiosity. Hidden in the depths of space, drifting silently through the cosmic dark, there's a pair of stars locked in an eternal dance, but one of them refuses to be seen. This is the phantom binary, a celestial mystery where one star shines bright while its companion remains completely invisible, swallowed by shadows, the only clue to its existence. The way its gravity bends the very fabric of space around it. Here's how it works. As the visible star moves, its unseen partner warps spacetime so intensely that light from distant galaxies behind them gets twisted and magnified, an effect called gravitational lensing. It's like holding a magnifying glass over a page, except the glass is made of pure gravity, and the page is the universe itself. Astronomers can't directly spot the hidden star, but they watch as distant starlight flickers and bends in unnatural ways, betraying the presence of something massive lurking just out of sight. Studying this ghostly duo is like trying to solve a puzzle with half the pieces missing. The obscured star emits no light, no heat, just an irresistible gravitational pull. Scientists have to rely on faint distortions in the light of other stars, like tracking a thief by the footprints they leave in the snow. Even then, cosmic dust and interference from other celestial objects can muddy the data, making it nearly impossible to confirm the hidden star's size, composition, or even its exact location. What makes the phantom binary so captivating isn't just its elusiveness, it's what it teaches us about the universe's hidden architecture. Most stars in the cosmos live in pairs or groups, but finding one that's completely invisible forces us to rethink how these systems form and evolve. Could there be countless other hidden stars out there, silently tugging on their brighter siblings? The answer might rewrite the way we map the galaxy, proving that sometimes the most important discoveries aren't what we see, but what we can't. Deep in the void between the stars, where temperatures plunge to near absolute zero, an invisible giant might be drifting right past us, one we'd never notice unless we knew exactly how to look. This is the dark dwarf, a failed star too massive to be a planet yet too small to ignite the nuclear fires of a true sun. It emits barely a flicker of visible light, radiating only a faint infrared glow, the dying whisper of heat left over from its birth billions of years ago. Brown dwarfs like this are cosmic ghosts, and spotting them is like trying to find a warm needle in an interstellar haystack. But astronomers have a trick. They scan the sky with infrared telescopes, hunting for tiny patches of warmth against the freezing backdrop of space. These telescopes act like night vision goggles for the universe, revealing objects too cold to shine but just warm enough to stand out against the darkness. The most famous of these, the Wide-Field Infrared Survey Explorer, has already catalogued hundreds of brown dwarfs, some chillingly close to our solar system. What's startling is just how many of these dark dwarfs might exist. For every star like our Sun, there could be several brown dwarfs lurking unseen. Some researchers even suggest they outnumber visible stars in our galaxy, forming a vast, hidden population that's been overlooked simply because they're so hard to detect. Imagine walking through a crowded room where half the people are invisible. That's the universe we're dealing with. Their stealthy nature makes them perfect candidates for explaining one of astronomy's biggest mysteries, dark matter. While brown dwarfs alone can't account for all the missing mass in the cosmos, they could be part of the puzzle. Every time we find one, it's a reminder that the universe is far stranger and far darker than it appears. These shadowy objects challenge our assumptions about what's normal in space, forcing us to ask, if we've missed something as basic as failed stars, what else is hiding just beyond our sight? Somewhere in the depths of space, a star is living on borrowed time, trapped in a deadly embrace with a black hole, circling so close that it's forever hidden from our view. This isn't just a cosmic game of hide and seek, it's a one-way trip into darkness. The star orbits just outside the black hole's event horizon, that infamous point of no return where even light gets sucked into oblivion. From our perspective, the star might as well not exist, yet its presence is betrayed by violent bursts of energy, like screams echoing from behind a locked door. What gives this hidden star away? X-ray flares, sudden, brilliant outbursts that flash across the universe like cosmic distress signals. As the star's outer layers get torn away by the black hole's gravity, they spiral inward, superheating to millions of degrees and releasing torrents of high-energy radiation. Telescopes can't see the star directly, but they catch these flares, painting a picture of a desperate struggle between gravity and momentum. It's like hearing the roar of a waterfall just beyond a dense fog. You know the water's there, even if you can't see it. The physics at play here pushes the limits of what we thought possible. The star isn't just orbiting, it's being stretched and squeezed by tidal forces, a process so extreme that astronomers call it spaghettification. Imagine a piece of taffy pulled thin until it snaps, except this taffy is a star, and the force pulling it is stronger than anything in our solar system. Some of its material gets swallowed by the black hole, but some gets flung outward at nearly the speed of light, creating jets of plasma that shine across the electromagnetic spectrum. What's haunting is how brief this dance might be. Over centuries or millennia, the star will lose more and more of itself, slowly consumed until nothing remains. Yet, even in its demise, it teaches us invaluable lessons. By studying these flares and jets, scientists can map the extreme environment near a black hole's edge, testing Einstein's theories, probing the nature of gravity itself, and uncovering secrets about how black holes grow. Every flicker of X-rays is a breadcrumb leading us deeper into the mystery, proving that sometimes the most important discoveries come not from what we see, but from the echoes of what we can't. Buried in a thick cosmic shroud, so completely hidden that not a single visible photon escapes, lies one of the universe's most paradoxical stars, a brilliant giant trapped in its own prison of dust. This isn't just any star, it's a cosmic titan, likely dozens of times more massive than our Sun, yet utterly invisible to optical telescopes. The dust cloud surrounding it isn't a wispy veil. it's a suffocating blanket dense enough to block even the most intense starlight. But here's the twist. This same dust that hides the star also betrays its existence, glowing faintly with the heat of its buried power source. To uncover this dust-shrouded giant, astronomers ditch traditional telescopes and turn to radio and submillimeter observatories. These instruments detect wavelengths far longer than visible light, piercing through the dust like X-rays through skin. What they reveal is staggering. A star so luminous that if not for its dusty cage, it would outshine most of its galactic neighbors. The dust itself becomes a messenger, absorbing the star's fierce radiation and re-emitting it as subtle thermal whispers, clues that scientists painstakingly decode to reconstruct the hidden colossus beneath. The star's environment is a chaotic nursery of creation and destruction. The same dust hiding it is also raw material for new planets, swirling in a maelstrom of gravity and radiation. Some of this material may one day coalesce into worlds, while the rest gets vaporized by the star's violent energy. It's a cosmic balancing act. Too much dust, and the star remains forever veiled. Too little, and its radiation would blast everything nearby into oblivion. What makes these dust-shrouded giants so fascinating is their role in galactic evolution. They're cosmic engines, forging heavy elements in their cores and seeding the galaxy with material for future stars and planets. Yet they spend their brightest moments hidden, their brilliance muted by the very matter they help create. It's a reminder that the universe often keeps its greatest marvels just out of sight, waiting for us to look not with our eyes but with our ingenuity. Most stars live out their lives in the crowded neighborhoods of galaxies, bound by gravity to siblings and neighbors. But not this one. Meet the rogue star, a lonely traveler hurled into the abyss of intergalactic space, where it drifts without a home, a path, or even a glimmer of companionship. This isn't just a star that wandered too far. It was violently ejected, flung away by gravitational forces so extreme that it escaped its galaxy entirely. Now it sails through the void at speeds that defy comprehension, a ghostly ember fading into the endless dark. What makes this star so impossible to spot isn't just its solitude, it's the sheer distance. Unlike stars hiding in dust clouds or orbiting black holes, this one is truly alone, with no nearby objects to reveal its presence through their interactions. Its light, already faint from the expulsion, has to travel millions of light years just to reach us, dimming to near invisibility along the way. Even our most powerful telescopes strain to catch more than a whisper of its existence. Yet astronomers have ways of tracking these cosmic fugitives. Sometimes they're betrayed by subtle shifts in color, a telltale sign of their high speed as they race away from their home galaxies. Other times, their trajectory gives them away. Like a bullet fired into the night, their path traces back to the scene of the crime, revealing the galactic collision or black hole encounter that sent them fleeing. But the most haunting question isn't how they got here, it's what happens next. A star without a galaxy has no reservoir of gas to form new planets, no stellar neighbors to light its way. It burns in perfect isolation, its eventual death as quiet and unseen as its life. Some may cool into dark cinders while others explode unnoticed, their final moments echoing across an empty universe. Yet these rogue stars aren't just cosmic anomalies, they're evidence of the universe's untamed violence. Every one we detect is a fossil record of some ancient cataclysm, a gravitational slingshot from events so powerful they can fling entire stars into the abyss. They force us to confront an unsettling truth. For all the order we see in galaxies and clusters, the cosmos is still a place of chaos where even stars aren't guaranteed a home. And somewhere out there, in the unimaginable vastness between galaxies, countless more of these lonely wanderers drift unseen, carrying stories we may never hear. In the violent aftermath of a supernova, where a massive star collapses into an ultra-dense neutron star, something even stranger can happen, a cosmic partnership so one-sided that one member vanishes into the other's shadow. Picture a neutron star spinning hundreds of times per second, its beams of radiation slicing through space like a lighthouse gone haywire. Now imagine it has a companion, a normal star orbiting perilously close, bathing in that deadly radiation. The neutron star's fury is so intense that it drowns out its partner entirely, rendering it invisible to conventional telescopes. This isn't just a hidden star, it's a star erased by its own neighbor's brilliance. The only way to detect this unseen companion, listen. Neutron stars like this often become pulsars, emitting rhythmic pulses of radio waves as they spin. But when they're locked in orbit with another star, something fascinating happens. Those pulses arrive slightly off schedule. The hidden star's gravity tugs on the pulsar, making its signal wobble in predictable ways. Astronomers track these minuscule timing variations like detectives decoding a tapped phone wire, reconstructing the invisible partner's mass, orbit, and even its rough composition. It's celestial forensics, uncovering what light alone can't reveal. What makes these systems so extraordinary is the sheer violence of their relationship. The neutron star's radiation isn't just hiding its companion, it's slowly destroying it. Stellar wind particles, accelerated to near light speed, blast the hidden star's surface, stripping away its atmosphere atom by atom. In some cases, this creates a shimmering halo of ionized gas around the pair, a ghostly fingerprint of the ongoing theft. Over millions of years, the neutron star might consume its partner entirely, leaving behind only a cold, dense remnant. Yet even in this lopsided dance, there's cosmic symmetry. The same radiation that obscures the companion also makes it detectable through its indirect effects. Without the pulsar's clockwork precision, we'd have no clue the star was there at all. It's a reminder that the universe often hides its secrets in plain sight, not behind barriers, but in the subtle distortions of the signals we can see. And somewhere out there, countless more of these invisible duos whirl in the dark, their stories written not in light, but in the silent pull of gravity. One of the universe's most baffling vanishing acts happened right in front of astronomers, and they still can't fully explain it. In 2009, a hypergiant star, 25 times more massive than our Sun and burning millions of times brighter, simply disappeared. No explosion, no dramatic supernova, not even a fading flicker. One moment it was there, lighting up its corner of the galaxy. The next, it was gone, as if someone had flipped a cosmic switch. This wasn't just any star, it was a luminous blue variable, a rare and unstable behemoth prone to violent outbursts. Yet when it vanished, it left behind no trace, no debris, not even a whisper of the catastrophic death throes we'd expect from a star of its size. The leading theory, it might have skipped the supernova entirely and collapsed directly into a black hole. A phenomenon so rare that it challenges everything we know about stellar deaths. Normally, when massive stars die, they go out with a bang, ejecting their outer layers in a brilliant explosion visible across galaxies. But in this case, the hypergiant could have imploded so abruptly that its outer layers fell inward too fast for radiation to escape. No light, no shockwave, just a quiet, unfathomable plunge into darkness. It's like watching a skyscraper vanish mid-collapse, leaving no rubble behind. But here's where it gets even stranger. Even if it became a black hole, we should have detected something. Black holes aren't perfectly invisible. They often announce their presence by devouring nearby gas or bending light from stars behind them. Yet follow-up observations found nothing, no X-ray flares, no gravitational lensing, no heat signature. The absence of evidence is as puzzling as the disappearance itself. Some scientists speculate the star might have dimmed rapidly behind a curtain of dust, but that doesn't explain why it didn't re-emerge. Others wonder if we witnessed a completely new kind of stellar death, one that defies our current models. The mystery of the vanishing hypergiant forces us to confront a humbling reality. For all our telescopes and theories, the universe still holds surprises that upend the rules. If stars this massive can disappear without a trace, how many others have done the same unnoticed? It's a reminder that the cosmos operates on scales and timelines we're only beginning to grasp, and that sometimes the most profound discoveries aren't about what we find, but what we lose. At the heart of our galaxy, where the Milky Way's supermassive black hole devours everything that strays too close, there's an entire cluster of stars hiding in plain sight, blotted out by the very forces that make them so fascinating. These aren't just any stars, they're packed so tightly around the black hole that they orbit at unimaginable speeds, some completing a full revolution in mere years. Yet despite their proximity to one of the most energetic regions in the galaxy, we'd have no idea they existed if not for one crucial detail: they shine in infrared. The problem is Sagittarius, a star, our galaxy's central black hole. Its surroundings are a maelstrom of dust and gas, swirling in a chaotic dance that blocks nearly all visible light. Traditional telescopes see only a murky void, as if the universe itself has drawn a curtain across the scene. But infrared light slips through where visible light cannot, its longer wavelengths unaffected by the same cosmic obstacles. By switching to infrared observations, astronomers pull back that curtain, revealing a stellar spectacle: dozens of stars whipping around the black hole like moths trapped in a whirlwind. The most remarkable of these hidden stars are the S-stars, a group orbiting so close to the black hole that they reach speeds of thousands of kilometers per second. Their paths aren't neat circles but extreme ellipses, looping wildly around the gravitational monster at their center. One star, known as S2, comes within just 17 light hours of the black hole at its closest approach, a hair's breadth in cosmic terms. At that distance, the forces are so intense that Einstein's theory of relativity comes into play, stretching the star's light into longer wavelengths and slowing its apparent time. Detecting these stars isn't just a triumph of technology, it's a window into how galaxies evolve. Their very existence is a puzzle. Stars shouldn't be able to form this close to a black hole's destructive grasp. Yet there they are, suggesting they either migrated inward over eons or formed in place under conditions we're only beginning to understand. Every flicker of infrared light from this hidden cluster carries clues about the Milky Way's violent past and the invisible forces sculpting its core. What's thrilling is how much we still don't know. With each new observation, astronomers uncover more stars in this secret dance, each one defying expectations. Some may be remnants of disrupted star clusters, others survivors of near misses with the black hole. Together, they paint a picture of a region far more dynamic and far more crowded than we ever imagined. And as telescopes grow more advanced, we're not just seeing these hidden stars, we're watching them move in real time, tracing the invisible hand of gravity itself. What if some stars aren't made of the stuff we know, not hydrogen, not helium, but something entirely invisible? Enter the most elusive phantom of all, the dark matter star, a cosmic enigma so strange it exists only in theory. Unlike ordinary stars that shine by fusing atoms, these hypothetical objects would be built from dark matter, the mysterious substance that makes up 85% of the universe's mass, yet refuses to interact with light. If they're out there, they'd be utterly undetectable to our telescopes, hiding in plain sight while shaping the cosmos around them. The idea hinges on a radical reimagining of stellar physics. Ordinary stars form when gas clouds collapse under gravity, heating up until nuclear fusion ignites. But dark matter behaves differently. It doesn't clump or collide like normal matter. Some theories suggest certain types of dark matter particles could interact weakly with each other, allowing them to accumulate in dense enough concentrations to form star-like structures. These wouldn't burn or shine. Instead, they'd generate heat through dark matter annihilation, a process where particles collide and release energy without producing light. Picture a furnace with no flame, a ball of pure, invisible energy radiating nothing but gravity. Why can't we find them? The answer lies in their very nature. Dark matter stars wouldn't emit photons, absorb them, or even cast shadows. The only way to infer their presence would be through their gravitational effects, perhaps bending light from distant galaxies subtly or distorting the orbits of visible stars nearby. Some researchers have combed through telescope data searching for unexplained gravitational anomalies, but so far, no smoking gun has emerged. The controversy around these invisible giants splits scientists. Skeptics argue that without direct evidence, dark matter stars remain speculative or fascinating. What if, without footing in reality? Others counter that their existence could solve lingering cosmic puzzles, like why some galaxies rotate faster than expected or why certain gravitational lensing events don't align with visible mass. If dark matter can clump into stars, it might also form other structures, dark planets, dark black holes, creating an entire invisible universe parallel to our own. What makes the concept so tantalizing isn't just its audacity, but its implications. Discovering a dark matter star would rewrite the rules of astrophysics, proving that the universe builds stars in ways we never dreamed possible. Until then, they linger at the edge of science, ghosts in the cosmic machine, waiting for someone to shine a light we can't even see. Some explosions in the cosmos leave more than just debris, they leave unanswered questions. In the case of one missing star, the mystery begins where it should have ended, with a supernova that never quite happened. This is the ghost of a supernova, a celestial puzzle where astronomers expected to find the remains of a massive star, only to discover nothing but empty space. The story starts with a supernova candidate, a star so massive its fate should have been a violent, brilliant death. Based on its observed brightness and behavior, scientists predicted it would explode, scattering heavy elements across the galaxy and leaving behind either a neutron star or a black hole. But when the moment came, the expected supernova never arrived. Instead, the star simply vanished. No blinding flash, no expanding shockwave, no glowing remnant. Just an absence where a star used to be. So what happened? One possibility is far stranger than a typical explosion. The star might have been devoured by an unseen companion before it could go supernova. Imagine a binary system where one star, a dense white dwarf or neutron star, orbited too close to its massive partner. As the doomed star approached the end of its life, expanding in its final stages, its companion could have siphoned off its outer layers, destabilizing it. Without enough mass to trigger the collapse needed for a supernova, the star's core might have fizzled, collapsing directly into a black hole without the usual fireworks. But there's another, even more unsettling explanation: that the star disintegrated through a process we don't fully understand. Some theorists speculate certain ultra-massive stars might undergo a phenomenon called pair instability, where their cores become so hot that matter and antimatter particles spontaneously form. This creates a runaway reaction that doesn't just explode the star, it annihilates it completely, leaving behind not even a black hole. If this occurred, it would explain the absence of any remnant, but it would also mean we're witnessing a type of stellar death so rare it borders on theoretical. The eerie part: both scenarios challenge our understanding of how stars die. Supernova are supposed to be predictable, the final, inevitable chapter for stars above a certain mass. Yet here we have a star that sidestepped the rules, either swallowed by a cosmic predator or erased by physics we've barely begun to comprehend. Every observation deepens the mystery, forcing astronomers to ask, if stars can vanish like this, how many others have done the same without us noticing? The universe may be hiding more ghosts than we thought. Imagine a light so blinding that it drowns out everything around it, not just nearby stars but entire galaxies. That's the paradox of a quasar, the universe's most luminous object. These cosmic beacons are powered by supermassive black holes feasting on gas and dust, so energetic that they outshine their host galaxies by a factor of 1,000. But buried beneath that brilliance, hidden in the glare, lies a secret, the quasar's host galaxy, packed with stars we can't see. This isn't just a case of brightness overpowering faint light, it's like trying to spot fireflies dancing in front of a spotlight. So how do astronomers peel back the quasar's glare to uncover these hidden stars? The trick lies in wavelengths our eyes can't see. Quasars blaze brightest in visible and ultraviolet light, but their host galaxies often emit more subtly in the infrared thermal radiation from countless cool, aging stars. By switching to infrared telescopes, scientists can effectively turn down the quasar's blinding output, revealing the faint glow of its galactic home. It's like putting on night vision goggles in a room flooded with fluorescent light. Suddenly, the hidden details emerge, but even then, separating the quasar's light from its host is a delicate puzzle. Advanced algorithms comb through the data, modeling and subtracting the quasar's signature to isolate the galaxy's residual light. Sometimes the galaxy's structure gives itself away, spiral arms or a central bulge warping the quasar's surrounding glow in telltale ways. Other times, gravitational lensing comes into play. If a massive object bends the quasar's light, it can magnify portions of the host galaxy, offering fleeting glimpses of stars that would otherwise stay invisible. What's astonishing is what these hidden stars reveal. Quasars aren't just random monsters, they're tied to galaxies evolving under extreme conditions. Some hosts are galactic train wrecks, their stars flung into chaotic orbits by violent mergers that also funneled gas into the central black hole. Others are surprisingly normal, suggesting quasars can ignite in relatively quiet neighborhoods. Each discovery challenges assumptions about how black holes and galaxies grow together, and how many more stellar populations might be hiding in plain sight, overshadowed by the universe's brightest giants. The deeper we look, the more we realize quasars aren't solitary anomalies. They're flashy symptoms of something far larger, galaxies undergoing dramatic transformations, their stories written not just in the black hole's fury, but in the quiet glow of stars we're only learning how to see. Deep within a frigid stellar nursery where temperatures hover just above absolute zero, a hidden star fights to be born, trapped in a cocoon so thick with ice and frozen gas that not a flicker of its light can escape. This isn't just another young star, it's a protostar in its earliest, most vulnerable stage, still gathering mass from the surrounding cloud. What makes it invisible isn't distance or darkness, but the very material that feeds it, a dense shroud of water ice, ammonia, and methane that blocks all visible light. To uncover it, astronomers must abandon conventional telescopes and turn to microwaves, the only wavelengths capable of piercing this frozen veil. Microwave observations reveal what optical telescopes cannot, the subtle heat signature of a collapsing core. As gravity pulls the surrounding gas and dust inward, friction heats the particles just enough to emit faint microwave radiation like the warmth of a handprint on a freezing window. Telescopes like the Atacama Large Millimeter Array in Chile detect these whispers of heat, mapping the protostar's structure in stunning detail. The data shows a swirling disk of material, with jets of gas erupting from its poles, telltale signs of a star fighting to free itself from its icy womb. The chemistry of this environment is just as fascinating as the physics. The cocoon's ice isn't pure water, it's laced with complex organic molecules, the building blocks of life. Some scientists speculate that these ices, once heated by the newborn star, could someday form the raw material for planets, or even the precursors to biological molecules. It's a cosmic irony. The same ice hiding the star might one day seed the ingredients for life elsewhere in its system. What makes these ice-enshrouded protostars so critical to study is their role in solving a stellar mystery: how stars like our Sun overcome their dusty beginnings. For every star we see shining brightly, there was once a phase like this, a hidden struggle against gravity and opacity, playing out behind an impenetrable curtain. By decoding the microwave signatures of these infant stars, we're glimpsing the universe's most intimate act of creation. Not the brilliance of a mature sun, but the quiet, invisible battle that makes it possible. Somewhere in the vastness of space, a star might exist that doesn't just hide, it disappears by turning the universe's own light against it. This is the mirror star, a theoretical celestial object made of exotic matter so perfectly reflective that it vanishes into the cosmic backdrop. Unlike stars obscured by dust or distance, this one wouldn't just dim or fade. It would become a flawless optical illusion, bouncing back every photon that hits it without absorbing or scattering a single ray. To an observer, it wouldn't just be invisible, it would be undetectable by conventional means, a cosmic chameleon disguised as empty space. The physics behind such a star bends the limits of reality. For a mirror star to exist, its surface would need to defy the laws of thermodynamics. Ordinary stars absorb some light and re-emit it as heat, but this hypothetical object would have to reflect every wavelength with zero loss, an impossibility with known materials. Yet some theories suggest exotic states of matter, like Bose-Einstein condensates or quark-gluon plasma, could achieve near-perfect reflectivity under extreme conditions. Picture a sphere so dense and cold that photons skid across its surface like stones on a frictionless pond, never penetrating, never warming it. Even more intriguing is how such a star might form. One hypothesis points to the early universe, where pockets of exotic matter could have condensed into stable structures before ordinary atoms existed. Another suggests a neutron star already incredibly dense might undergo a phase transition, its surface crystallizing into a perfect mirror under unimaginable pressure. The catch: any imperfection, even at the atomic level, would shatter the illusion, scattering enough light to betray its presence. Detecting a mirror star would require rethinking astronomy itself. Traditional telescopes rely on light emission or absorption, but a flawless reflector would leave no such fingerprints. Instead, scientists might hunt for distortions in the cosmic microwave background, anomalies where the afterglow of the Big Bang appears subtly warped around nothing. Alternatively, gravitational lensing could reveal its mass-bending light from distant galaxies while remaining optically silent. The mirror star isn't just a scientific curiosity, it's a challenge to our assumptions about what's possible. If such objects exist, they'd rewrite the rules of visibility, proving that the universe's greatest tricks aren't about hiding in darkness but in plain sight. Stretching the limits of physics to their breaking point, one star races through the cosmos at a significant fraction of light speed, so fast that the universe itself struggles to keep up. This is the time-dilated star, a celestial speedster moving so rapidly that its light gets stretched into oblivion by the sheer force of its velocity. According to Einstein's theory of relativity, as an object approaches the speed of light, time slows down for it relative to the rest of the universe. For this star, that means the light it emits gets redshifted, pulled into longer, invisible wavelengths like a cosmic Doppler effect taken to the extreme. What should be a blazing beacon in the night sky becomes a whisper in the radio silence of space, its photons stretched so thin that even our most sensitive telescopes might never detect them directly. But here's the catch: while its light may fade into the background, its gravity refuses to stay hidden. Every massive object warps the fabric of spacetime around it, and this star is no exception. As it streaks across the galaxy, it tugs on nearby stars and gas clouds, leaving behind subtle gravitational ripples in its wake. Astronomers can track these disturbances, minute deviations in the motion of visible objects like following the trail of a ghost. In some cases, the star's gravity might even bend light from more distant stars behind it, creating a fleeting lensing effect that betrays its position without revealing its light. It's a cosmic game of hide and seek where the hider leaves footprints in the very fabric of reality. What makes this star so fascinating isn't just its speed, but what it teaches us about the extreme edges of physics. Most stars move at a leisurely pace relative to their galactic neighbors, but this one could be a cosmic outlier, a runaway star ejected from a violent event like a supernova or a close encounter with a black hole. Some might even be remnants of binary systems where one star exploded, flinging its partner into the void at unimaginable speeds. Others could be travelers from outside our galaxy, hurtling through intergalactic space like bullets fired from an unseen gun. The real challenge lies in proving their existence. Without detectable light, astronomers have to rely on indirect signatures, anomalies in stellar motions, unexplained microlensing events, or even distortions in the cosmic microwave background. Each clue is like a single brushstroke in an invisible painting, hinting at a picture we can't yet see. But if we do find one, it could open doors to new tests of relativity, helping us understand how matter behaves under the most extreme conditions the universe has to offer. And that's the paradox of the time-dilated star. It's both a shadow and a revelation. Hidden by the very laws that make it unique, it challenges us to look beyond light, beyond conventional detection, and into the subtle gravitational whispers of the cosmos. For all we know, these relativistic phantoms might be streaking past us right now, rewriting the rules of visibility in their silent, high-speed flight. Somewhere in the void, light itself is being stolen not by a black hole, but by a cosmic thief made of dust and gas. Meet the cosmic chameleon, a star so perfectly camouflaged by an intervening nebula that it doesn't just blend into the darkness, it vanishes without a trace. Unlike stars obscured by distance or their own faint glow, this one is swallowed whole by its surroundings, its light absorbed before it can reach us. Yet despite its flawless disguise, astronomers know it's there, because the nebula itself holds clues too glaring to ignore. The telltale sign, anomalies in the nebula's spectrum, strange spikes and dips in the wavelengths of light passing through it. Normally, nebulae absorb specific frequencies depending on their composition, like a filter blocking certain colors. But when scientists studied this particular cloud, they found absorption lines that didn't match any known elements in interstellar space. The culprit, a hidden star's light filtered and altered by the nebula's grasp. It's like hearing a voice through a wall. You might not see the speaker, but the muffled sound proves they're there. Here's how the trick works. As the star's light tries to escape, it slams into the nebula's dense particles. Some wavelengths get absorbed completely, while others scatter in random directions. The result is a spectral fingerprint unlike anything a nebula alone could produce. Hints of ionized metals, unexpected energy signatures, and even traces of ultraviolet radiation that shouldn't exist in such a cold, dark cloud. By reverse engineering these anomalies, astronomers can reconstruct the star's temperature, size, and even its likely lifespan, all without catching a single direct photon. The nebula isn't just a curtain, it's a translator. In some cases, the cloud's molecules get excited by the hidden star's radiation, re-emitting light at entirely new wavelengths. Telescopes tuned to these secondary emissions can map the nebula's glow like an X-ray revealing bones beneath skin. Infrared observations, meanwhile, might catch heat from dust grains warmed by the star, tracing its outline like a shadow puppet against a backlit screen. What makes the cosmic chameleon so fascinating isn't just its stealth. It's the way it forces us to rethink how we map the universe. For every star we see, there could be dozens more hiding behind these interstellar veils, their presence betrayed only by the faintest distortions in the cosmic static. And as telescopes grow more sensitive to these whispers, we're peeling back layer after layer of celestial camouflage, discovering that the night sky isn't just what shines, it's what refuses to be seen. Some stars don't just die, they come back. Lurking in the wreckage of a cataclysmic supernova, a cosmic anomaly refuses to fade away. The zombie star, a stellar remnant that somehow survived its own violent death. This isn't a ghost or an illusion, it's a real, physical object, hidden beneath layers of ejected material and defying everything we thought we knew about how stars end. Most massive stars explode with enough force to obliterate themselves completely, leaving behind either a neutron star or a black hole, but this one, it's still there, battered and bruised, clinging to existence in a shell of its former self. The first clue that something was unusual came from the supernova itself. When astronomers observed the explosion, something didn't add up. The energy output was too low, the light curve too erratic. Normally, a supernova's brightness follows a predictable pattern as radioactive elements in the ejector decay. But this one flickered inconsistently, as if the star had only partially detonated. Then, years later, follow-up observations revealed the unthinkable: a persistent heat source buried in the debris field, glowing faintly in infrared. It was as if the star had left a piece of itself behind, a smoldering ember in the ashes of its own destruction. How does a star survive a supernova? The leading theory involves a phenomenon called pulsational pair instability. In this scenario, the star's core becomes so hot that it starts producing matter and antimatter pairs, triggering violent eruptions that blast away its outer layers without fully destroying it. Think of it like a bomb with a faulty fuse. Instead of detonating all at once, it erupts in fits and starts shedding enough mass to avoid total collapse. The result is a star that's technically dead, its core exposed and inert, yet still shining dimly through the chaos it created. The real mystery, though, isn't just how it survived, it's where it's hiding. The zombie star is buried so deep in its own debris that even our most powerful telescopes struggle to pick it out from the surrounding glow. To find it, astronomers rely on subtle hints, unusual chemical signatures in the ejector, or faint echoes of ultraviolet light bouncing off the surrounding gas. It's like trying to spot a flashlight through a blizzard. The beam might be weak, but its reflection on the snowflakes gives its position away. What fascinates scientists isn't just the star's defiance of stellar life cycles, but what it suggests about supernova as a whole. If stars can partially explode, leaving behind remnants we never anticipated, how many other failed supernova have we missed? Could there be an entire population of these cosmic undead, lurking unnoticed in the wreckage of past explosions? The zombie star forces us to reconsider the boundaries between life and death in the cosmos, proving that sometimes the universe's most profound secrets aren't just about what dies, but what refuses to stay dead. Isolated in a galaxy so devoid of ordinary matter that telescopes see only darkness, a single star burns against impossible odds, the last beacon in an empire of shadows. This isn't just a star hidden by distance or dust. It's a cosmic anomaly trapped in a dark galaxy, a realm where invisible matter outweighs everything else by thousands to one. Most galaxies glitter with countless stars, but here, this lone survivor shines amidst a sea of dark matter, defying every rule we know about how stars form and endure. The mystery begins with the galaxy itself. Dark matter galaxies are thought to be ancient relics from the early universe, pockets where normal matter, gas, dust, the ingredients for stars, never quite gathered in enough quantities to ignite stellar birth. Yet somehow this solitary star exists. One theory suggests it's a runaway, hurled into the dark galaxy by a violent encounter long ago, perhaps ejected during a collision between two ordinary galaxies, left to wander until it was captured by the dark matter's gravity. If so, its journey would have been a solitary one, drifting for millions of years before settling into this eerie expanse. But there's another, wilder possibility. Maybe the star formed here against all odds. Dark matter's gravity could have slowly drawn in wisps of hydrogen over eons, concentrating just enough gas in one spot to trigger a single, fragile star's birth. It's like a single match flaring in a rain-soaked forest, statistically improbable, but not impossible. The star's composition might hold clues. If it's rich in primordial elements, hydrogen and helium with almost no heavier metals, it could hint at formation from nearly pure, ancient gas untouched by generations of earlier stars. Yet survival is an even greater puzzle. Stars in empty environments lack the protective cocoon of a galaxy's magnetic fields and gas clouds, leaving them exposed to cosmic rays and interstellar winds. Without neighboring stars to stabilize its orbit or replenish its surroundings, this lone star should have faded or been torn apart by now. The fact that it persists suggests something extraordinary, perhaps a dense halo of dark matter shielding it, bending destructive forces away like an invisible force field. The implications are staggering. If one star can exist in such isolation, others might too, scattered across the cosmos in galaxies too dim to detect. Every flicker of light in these dark realms challenges our understanding of how structure forms in the universe. Are these stars accidents, or do they hint at processes we've yet to imagine? For now, this solitary beacon keeps its secrets, a flickering question mark in the dark. Deep in the cosmic void, a star hides in the ultimate game of stealth, emitting no light, no heat, not even the faintest radio whisper. Yet its presence is undeniable, written into the very fabric of space by the one force nothing can escape: gravity. This isn't just an invisible star, it's a gravitational echo, a phantom whose existence we know only because it bends the universe around it like a hidden weight on a trampoline. The key to detecting these unseen giants lies in a phenomenon called gravitational microlensing. Here's how it works. When the invisible star passes between Earth and a more distant, visible star, its gravity warps spacetime, acting like a cosmic magnifying glass. The background star's light doesn't just dim, it brightens momentarily as the hidden star's gravity focuses the light toward us. It's as if the universe itself is winking at us, a fleeting signal that something massive just crossed our line of sight. These events last mere days or even hours, requiring telescopes to scan millions of stars continuously to catch them in the act. Some of the most compelling evidence for these dark stars comes from projects like the optical gravitational lensing experiment, which has catalogued thousands of microlensing events over decades. A handful stand out: mysterious lensing signatures with no visible counterpart. One particularly famous case involved a lensing object roughly half the mass of our Sun, yet completely dark. Was it a rogue planet, a failed star, or something stranger? Follow-up observations ruled out planets or brown dwarfs, leaving astronomers with a tantalizing possibility: a lone neutron star, cold and dark after billions of years, drifting silently through the galaxy. The implications are staggering. If stars like this exist, they could be remnants of the early universe, stellar ghosts from a time before galaxies took shape. Some might even be primordial black holes, formed not from dying stars but in the chaos of the Big Bang itself. Others could be neutron stars that burned through their residual heat, fading into invisibility but still bending light with their immense density. Every microlensing event is a clue, a breadcrumb leading us toward a hidden population of objects that defy conventional detection. What's most exciting is how these discoveries challenge our assumptions. We think of the cosmos as a place of light and darkness, but gravitational echoes remind us that some of its most important players operate in perfect silence. They don't just hide, they redefine what it means to be unseen. And with every new microlensing survey, we're peeling back another layer of the universe's best-kept secrets. Sometimes stars don't reveal themselves, they're exposed by the worlds orbiting them. Deep in the constellation Cygnus, astronomers have found something extraordinary: a planet with no visible sun. This isn't a rogue world drifting through the void, it's a transiting exoplanet, one that periodically dims the light of a background star as it passes in front. But here's the twist: the star it should be orbiting, it's nowhere to be found. This is the Phantom Exoplanet Host, a celestial detective story where the star is the missing person and its planet is the only clue. The discovery began with data from telescopes like Kepler, which monitor stars for the telltale dips in brightness caused by orbiting planets. In this case, the planet's transit signal was clear, regular, predictable, textbook. But when astronomers pointed other telescopes at the spot, searching for the parent star's light, they found nothing. No infrared glow, no visible spectrum, not even a flicker of radio waves. The planet was there, transiting something, but the something refused to show itself. It's like watching a shadow puppet show where the puppet's visible, but the hand casting it is completely invisible. So how do you lose an entire star? One possibility is that it's buried in an unusually dense cloud of interstellar dust, so thick that it absorbs virtually all the star's light before it can reach us. Imagine a spotlight shining through a blackout curtain. The light's there, but the fabric swallows it whole. Another theory suggests the star might be a white dwarf or neutron star, remnants of stellar death so faint that even our best telescopes struggle to spot them at interstellar distances. But here's the catch. Most known planets around such stars orbit perilously close, and this planet's transit duration suggests a much wider orbit, defying expectations. The most tantalizing explanation, though, is that we're seeing a star in the process of vanishing. Some models predict that in rare cases, massive stars on the verge of collapsing into black holes might expel their outer layers so violently that they temporarily shroud themselves in a cocoon of debris, rendering them invisible for centuries. If this planet's host is in that brief, catastrophic phase, we might be witnessing a cosmic magic trick in progress. A star disappearing while its planet, oblivious, continues its endless loop around nothing. The hunt for this phantom star isn't just academic, it's a test of how we understand planetary systems. If stars can hide so completely, how many others have we missed? Could there be entire populations of planets orbiting unseen suns, their existence only revealed when they pass in front of brighter background stars? Every unexplained transit is a breadcrumb, leading us toward a universe far stranger than we imagined, one where even the most fundamental relationships, like a planet and its star, might not be what they seem. In the cosmic dance of binary stars, sometimes the waltz turns predatory. Picture two stars locked in orbit, but one isn't just a partner, it's a thief slowly draining the life from its companion. This is the cosmic vampire, a binary system where a dense neutron star or white dwarf siphons material from its neighbor, cloaking the victim in swirling chaos. The donor star isn't just dimmed, it's buried under an accretion disk of its own stolen matter, a glowing shroud that renders it nearly invisible. What remains visible isn't the star itself, but the aftermath of the robbery, a telltale eruption of X-rays blazing across the universe. The violence of this theft is staggering. As the vampire star's gravity rips gas from its companion, the stolen material spirals inward at nearly light speed, superheating to millions of degrees. The result, a torrent of high-energy X-rays, so intense they pierce through cosmic dust and gas like a beacon. Telescopes like NASA's Chandra X-ray Observatory catch these emissions, mapping the accretion disk structure with precision. The data reveals a story of extremes: shockwaves from infalling material, magnetic fields twisting the disk into knots, and occasional eruptions brighter than entire galaxies. It's cosmic surgery, with the donor star's mass as the patient. But here's the twist: the victim isn't passive. Some donor stars fight back, their magnetic fields channeling stolen material into jets that blast outward like cosmic fire hoses. Others pulsate unpredictably, their instability disrupting the accretion flow in ways that baffle astronomers. Even the vampire star isn't invincible. If it gorges too quickly, the influx of material can trigger thermonuclear explosions on its surface, lighting up the system like a stellar flare gun. What makes these systems so mesmerizing isn't just their brutality, it's their role as cosmic laboratories. By studying X-ray emissions, scientists can measure the spin of neutron stars, test general relativity in extreme gravity, and even trace the origin of heavy elements forged in the accretion disk's furnace. Every flicker of X-rays is a clue, a line of code in the universe's most dramatic physics simulation. And somewhere out there, countless more of these hidden duels rage unseen, their stories written not in light, but in the high-energy screams of stolen starlight. One of the most baffling cosmic disappearances happened right under our telescopes, where a red giant star, billions of years old and impossible to miss, simply blinked out of existence. This wasn't some faint, distant speck. It was a massive, evolved star in the later stages of its life, the kind that typically ends in a spectacular supernova. Yet when astronomers revisited its location, they found nothing but empty space. No explosion, no remnant, not even a fading ember. The star had pulled off the ultimate vanishing act, leaving behind only questions. So what could erase a red giant without a trace? One possibility is a quiet collapse, an implosion so sudden and total that the star skipped its fiery death entirely. Red giants are supposed to shed their outer layers in a planetary nebula before their cores shrink into white dwarfs. But if conditions were just right or just wrong, this one might have bypassed the usual drama. Imagine a building demolishing itself from the inside, collapsing inward so efficiently that no debris escapes. That's the kind of silent catastrophe scientists suspect might have happened here, with the star's core crumpling straight into a black hole without the usual fireworks. But there's another, even wilder explanation. What if something flung it away? Galactic dynamics can be chaotic, especially near dense regions like the Milky Way's center. A close encounter with another massive object, a rogue black hole perhaps, or a cluster of neutron stars, could have slingshotted the red giant out of its orbit at incredible speed. Stars ejected this way become hypervelocity runaways, streaking through intergalactic space so fast that they leave their old neighborhoods behind in cosmic seconds. By the time we noticed it was missing, the star could already be halfway to another galaxy, its light stretched and redshifted into invisibility, the eerie part. Both scenarios challenge our understanding of stellar life cycles. If stars can implode without warning, how many others have done the same without us noticing? And if unseen forces can yank stars clean out of their homes, what else lurks in the dark, capable of rearranging the cosmos on a whim? Every missing giant is a reminder that the universe still holds mysteries no telescope can pierce, not because they're too faint, but because they leave no trail at all. Some stars don't just die, they're murdered. And in the case of one doomed celestial object, the killer leaves behind a trail of radiation instead of fingerprints. This is the victim of the Black Widow pulsar, a neutron star spinning so fast and blasting so much energy that it's slowly evaporating its companion into oblivion. What makes this cosmic crime scene so chilling isn't just the violence, it's how perfectly the pulsar hides the evidence, erasing its partner from the sky until only gravity's faintest whisper remains. The Black Widow pulsar gets its name from its gruesome feeding strategy. Like its arachnid namesake, it consumes its mate, a star that once orbited in peaceful harmony. But as the pulsar's beams of high-energy radiation sweep across space, they strip away the companion's outer layers atom by atom, creating a shimmering halo of superheated gas. Over millions of years, this relentless assault has reduced the star to a shadow of its former self, a dim, shrunken core barely clinging to existence. Today, it's too faint to detect with optical telescopes, its light drowned out by the pulsar's brilliance, yet the victim's presence isn't entirely erased. Like a ghost tugging at the edges of reality, its gravity still warps the pulsar's spin in subtle, detectable ways. Pulsars are nature's most precise clocks, their rhythmic beams arriving with near-perfect regularity. But when an unseen companion tugs on them, those ticks fall slightly out of sync, delayed by microseconds as the star's gravity bends space-time around the pulsar. By tracking these minuscule timing anomalies, astronomers can reconstruct the hidden star's mass, orbit, and even its grim fate. It's celestial forensics piecing together a murder from the killer's own heartbeat. What's even more astonishing is the scale of this destruction. The pulsar's radiation doesn't just chip away at the star, it bombards it with particles accelerated to nearly light speed, heating its surface to tens of thousands of degrees. Some of this stolen material gets whipped into jets shooting into space, while the rest spirals onto the pulsar's surface, triggering X-ray bursts bright enough to outshine entire star systems. The victim isn't just fading, it's being unmade in a storm of energy so intense it defies earthly analogies. The Black Widow's story forces us to confront a brutal truth about the cosmos. Not all stellar deaths are solitary. Some stars meet their end in the grasp of something far hungrier, their light snuffed out not by time but by a partner turned predator. And somewhere out there, countless more of these invisible duos may be locked in similar dances, one star blazing, the other dissolving, their tragedy written not in light but in the silent mathematics of gravity. At the farthest edge of theoretical physics, where even the most wild cosmic ideas begin to fray, there might exist a star unlike any other, one that doesn't just hide but actively repels our attempts to find it. This is the dark energy star, a hypothetical monster fueled not by nuclear fusion or gravity, but by the most mysterious force in the universe, dark energy itself. If such a thing exists, it wouldn't just be invisible, it would be actively erasing its own presence, expanding space around it so rapidly that light from its surface could never reach us. The concept bends known physics to the breaking point. Dark energy, the enigmatic force driving the universe's accelerating expansion, is supposed to be diffuse, evenly spread across the cosmos. But some models suggest it might, under conditions we can barely imagine, clump into concentrated pockets, creating regions where space stretches faster than anywhere else. Picture a bubble inflating from the inside, its surface racing outward so quickly that nothing, not even light, can keep up. A star trapped inside such a bubble would be forever beyond observation, not because it's dim or obscured, but because the space between us and it is growing faster than photons can cross it. Yet even if it's invisible, its effects might not be. One telltale sign could be gravitational lensing, subtle warping of background starlight as if from a massive object we can't see. But here's the twist. Unlike a black hole's sharp lensing, a dark energy star's expansion would distort light in bizarre ways, smearing galaxies behind it into unrecognizable streaks. Another clue might come from its interaction with cosmic voids, massive, nearly empty regions of space that already puzzle astronomers. If dark energy stars exist, their repulsive gravity could be actively pushing matter away, sculpting these voids into even larger, emptier expanses. The most unsettling possibility, these stars might not just be hiding, they could be rewriting cosmic history. If dark energy can clump into stellar-scale objects, it means the force isn't as uniform as we thought, throwing a wrench into our models of the universe's fate. Instead of a slow, cold death where galaxies drift apart, the cosmos could be dotted with these invisible accelerators, each one a time bomb of expansion, silently shredding the fabric of reality around it. Of course, this is all speculation at the farthest frontier of science. No telescope has ever detected a dark energy star, and many physicists argue the math simply doesn't allow for such objects. But the mere idea forces us to confront how little we truly grasp about the universe's darkest secrets. After all, if stars can exist that warp the rules of space itself, what else might be lurking in the vast, uncharted dark, drifting through the endless dark between galaxies, where distances stretch so vast that even light seems to lose hope? There's a star that doesn't belong, a cosmic castaway flung into the abyss. This isn't just any wandering star. It's an intergalactic runaway, a solitary exile hurled from its home galaxy with such violence that it now sails through the void at speeds that defy comprehension. Alone in the unimaginable emptiness, its light is so faint that our most powerful telescopes see only darkness where it travels. Yet its story is written in the scars of its expulsion, a tale of gravitational slingshots and galactic collisions that left it stranded in the coldest, emptiest reaches of the cosmos. The journey of this star reads like a cosmic thriller. Most likely, it was once part of a binary system orbiting peacefully in its galaxy, until a close encounter with a supermassive black hole at the galaxy's core tore it free. As the black hole's gravity snatched its companion, the surviving star was catapulted outward like a stone from a sling, reaching velocities high enough to escape its galaxy entirely. Now it drifts through intergalactic space, where the nearest neighbor might be millions of light years away, its faint glow stretched and redshifted by the relentless expansion of the universe itself. Detecting such a star borders on the impossible with today's technology. The Hubble Space Telescope, for all its power, would strain to spot even the brightest of these runaways, their light diluted by distance and the void's perfect blackness. But astronomers aren't giving up. Upcoming observatories like the James Webb Space Telescope and the Vera C. Rubin Observatory, with their unprecedented sensitivity to infrared and faint light, might finally pierce the gloom. These instruments could catch the star's infrared signature, its heat, faint but persistent, like the last ember of a dying campfire. Even then, confirmation would hinge on tracing its trajectory backward, reconstructing the ancient catastrophe that sent it fleeing. The real excitement lies in what these intergalactic runaways could teach us. Each one is a fossil record of its home galaxy's most violent events, collisions, black hole encounters, or even encounters with dark matter structures we've yet to map. Their compositions could reveal the chemical makeup of their parent galaxies from eras long before Earth existed. And if future telescopes find more of them, they might hint at a hidden population of stars adrift in the void, far larger than we ever imagined. But the most haunting possibility, some of these runaways might not be entirely alone. If planets orbited them before their expulsion, those worlds could have survived the journey frozen, dark, and drifting alongside their exiled suns. Imagine Earth-like worlds untethered from any galaxy, where the night sky holds no stars, no Milky Way, only an endless black expanse. It's a reminder that the universe's greatest dramas often play out unseen, and that even in the void there are stories waiting to be told, if only we learn how to listen. Deep in the heart of a binary star system, where one star shines brightly and the other doesn't, lurks the ghostly white dwarf, an ancient stellar corpse so cold it's nearly invisible. This isn't just a burned-out remnant, it's a cosmic stealth expert fading into the background of space until its gravity gives it away. Most white dwarfs glow faintly from residual heat, but this one has cooled over billions of years, its surface temperature dropping so low that it emits almost no light whatsoever. If not for the restless movements of its companion, we'd never know it was there at all. The key to uncovering this hidden relic lies in the subtle wobbles of its partner. Imagine a dancer spinning gracefully, yet occasionally tugged off balance by an unseen hand. That's what happens to the visible star in this system. As the white dwarf orbits, its gravitational pull tugs the brighter star back and forth, creating tiny but measurable shifts in its light. Astronomers call this the radial velocity method, and it's how we've detected countless invisible objects from exoplanets to dead stars. By tracking these rhythmic stellar stumbles, scientists can calculate the white dwarf's mass, orbit, and even its rough age, all without ever seeing it directly. But here's where it gets eerie. This white dwarf isn't just cold, it's practically fossilized. Most stellar remnants eventually crystallize as they cool, their carbon and oxygen interiors forming a lattice structure akin to diamond. Yet this one has gone even further, radiating so little energy that it's approaching the theoretical floor for stellar temperatures. In cosmic terms, it's a ghost, its presence inferred only through its lingering influence on the living. What makes the ghostly white dwarf so fascinating isn't just its stealth, but what it reveals about the universe's timeline. Stars like this are the end game of stellar evolution for most Sun-like stars, and their cooling rates act as cosmic clocks. By studying how this one has faded, astronomers can piece together the history of its system, tracing back to when it was still a vibrant star lighting up the cosmos. It's a reminder that even in death, stars leave behind clues not in the light they emit, but in the silent, gravitational echoes of their past. In the vast cosmic theater of illusion, one star performs the ultimate magic trick, appearing in multiple places at once while its true self remains unseen. This is the cosmic mirage, a celestial spectacle where gravity itself twists reality into a hall of mirrors. The star's light doesn't travel straight to us. Instead, it bends around a massive object, a galaxy or black hole, creating duplicate images scattered across the sky like scattered puzzle pieces. These aren't just faint echoes, they're perfect, bright replicas, each one a distorted snapshot of the same star frozen at different moments in time. The phenomenon, called gravitational lensing, is one of Einstein's most dramatic predictions in action. When light passes near an object with enormous gravity, spacetime curves, forcing photons to take a detour. If the alignment is just right, the result is a cosmic funhouse mirror, producing multiple images, stretched arcs, or even perfect rings of light. The cosmic mirage takes this to the extreme, its true position hidden behind the lens, while its doppelgangers shimmer elsewhere, some older, some younger, depending on the path their light took to reach us. But here's where the mystery deepens. Not all lensed stars are created equal. Some mirages flicker unpredictably because the lensing object, often a rogue planet or a dense star cluster, moves across our line of sight. Others change brightness as interstellar gas drifts between us and them, adding yet another layer of distortion. Astronomers have to play detective, untangling which images belong to the same star and reconstructing its true location from fragments of light. It's like solving a crime where the suspect's reflection appears in 3 different mirrors, each showing a slightly different angle. The most famous example: a star nicknamed Icarus, whose light was magnified over 2,000 times by a foreground galaxy cluster. For a brief moment, it became visible across 9 billion light-years, a flashbulb in the cosmic dark, until the lensing alignment shifted and it vanished again. But for every Icarus we catch, there are countless others still hiding, their true forms masked by the universe's own sleight of hand. What makes these mirages so invaluable isn't just their strangeness, it's what they reveal about the invisible masses warping space around them. By studying the distortions, astronomers can map dark matter, weigh distant galaxies, and even test the very fabric of spacetime. Each false image is a clue, a breadcrumb leading us closer to the universe's best hidden secrets. And somewhere out there, another star's light is bending around an unseen giant, waiting for us to decode its reflection. Tucked behind a cosmic curtain of interstellar dust so thick it blots out all visible light, an entire city of stars burns unseen, their combined glow reduced to a faint infrared whisper. This is the dark star cluster, a celestial metropolis hiding in plain sight, its existence betrayed only by the warmth leaking through its dusty shroud. Unlike lone hidden stars that vanish behind individual veils, this cluster's challenge is scale, mapping not just one obscured object but hundreds, all piled together in a space where traditional telescopes see only darkness. To peel back this dusty veil, astronomers turn to infrared observatories like the James Webb Space Telescope, which sees the universe in heat signatures rather than light. Imagine trying to map a bustling nighttime city during a blackout. Ordinary cameras would show nothing, but thermal goggles would reveal the warmth of buildings, cars, and people. That's how infrared telescopes expose the dark star cluster. Each star's heat pierces the dust, painting a ghostly outline of the cluster's structure. The youngest stars, still swaddled in their birth cocoons, glow brightest in these wavelengths, while older giants flicker like embers in the cosmic gloom. But mapping this hidden metropolis is no easy feat. The dust isn't a uniform blanket, it's a chaotic, swirling fog, denser in some regions than others. Light from stars at the cluster's core must fight through more layers, dimming and distorting their signals. Astronomers have to reconstruct these stars' true positions and brightness levels like detectives piecing together a crime scene from smudged fingerprints. Algorithms analyze how the dust scatters infrared light, reverse engineering the cluster's three-dimensional layout. Sometimes the data reveals surprises entire subgroups of stars displaced by ancient collisions or drifting together in unexpected orbits, hinting at a turbulent past. What makes the dark star cluster so extraordinary isn't just its invisibility, it's what it tells us about stellar nurseries we've long misunderstood. Many of the universe's most active star-forming regions are shrouded in similar dust, meaning we've likely underestimated the number and scale of these clusters. Some could be churning out stars at rates that defy our models, hidden behind walls of cosmic soot. Others might house rare, massive stars in their infancy, their growth spurts obscured until they suddenly emerge from the dust like giants stepping from the mist. And then there's the bigger picture. These clusters may hold clues to galactic evolution. The dust hiding them isn't just an obstacle, it's raw material for future stars and planets, a reminder that invisibility and creation often go hand in hand. Every photon of infrared light escaping the dark star cluster carries a message. The universe's grandest factories often operate in the dark, their secrets written not in the light we see, but in the heat we're only learning to trace. Somewhere in the vast expanse of the cosmos, a star is moving with such unimaginable speed that it's no longer part of our galaxy. It's a runaway on an interstellar highway, ejected with such force that it crossed the galactic frontier before we even knew it existed. This is the phantom hypervelocity star, a celestial fugitive moving so fast that its own home galaxy couldn't hold onto it. Clocking in at speeds exceeding 1,000 kilometers per second, it's not just drifting away, it's escaping the Milky Way's gravitational grip entirely, destined for the void between galaxies. So how does a star reach such extreme velocities? The most plausible explanation involves a close encounter with our galaxy's central supermassive black hole, Sagittarius A. In this scenario, the star was once part of a binary system that wandered too close to the black hole's event horizon. As the black hole's gravity captured one star, the other was slingshotted outward at a significant fraction of the speed of light, like a cosmic catapult hurling a stone into the abyss. Other theories suggest it might have been ejected by the shockwave of a nearby supernova, or even flung out during a violent galactic collision billions of years ago. The real challenge isn't just understanding how it escaped, it's reconstructing its path backward to uncover its origin. Without direct observations before its departure, astronomers must rely on forensic astronomy. By measuring its current velocity and trajectory, they can simulate its possible routes through the Milky Way, tracing gravitational interactions like breadcrumbs leading home. This involves supercomputer models that account for the galaxy's ever-shifting mass distribution, dark matter's invisible pull, and even the gravitational nudges from passing star clusters. It's celestial detective work at its finest, piecing together a star's ancient journey through a galaxy that no longer holds it. But here's the twist, this star might not be alone. Recent surveys suggest dozens, perhaps hundreds of hypervelocity stars are streaking through intergalactic space, each with its own story of expulsion. Some could be relics of ancient galactic mergers, their trajectories encoding the violence of long-ago collisions. Others might be travelers from dwarf galaxies torn apart by the Milky Way's gravity, their stars scattered like debris from a cosmic wreck. If we can map enough of these runaways, they could serve as a new kind of galactic archaeology, revealing events so old that light from their era has long since faded. What's most haunting is the fate awaiting these exiled stars. The space between galaxies is a desert cold, empty, and brutally vast, with no new sources of gas or dust to form planets, no neighboring stars to light their way, they'll burn out in isolation, their deaths as silent as their escape. Yet even in their solitude, they carry a message. The universe is far more dynamic and far more violent than it appears. Some stars don't just fade, they flee, leaving behind only gravity's faintest fingerprints as proof they were ever there at all. Imagine a star that defies the very laws of classical physics, not hidden behind dust or distance, but existing in a state of quantum uncertainty, flickering between locations like a cosmic magic trick. This is the quantum star, a theoretical marvel where the rules of the very small collide with the colossal scales of astrophysics. According to quantum mechanics, particles can exist in multiple states at once, a phenomenon called superposition, until observed. But what if an entire star could enter this bizarre condition? The implications would rewrite our understanding of reality itself. The foundation for this wild idea comes from cutting-edge theories like quantum gravity, where physicists attempt to bridge the gap between Einstein's relativity and the probabilistic world of quantum particles. In labs on Earth, we've seen electrons, photons, and even molecules occupy superposition states, but scaling this up to a star, a massive, seething ball of plasma, seems impossible. Gravity alone should collapse such a system into a single, observable state. Yet some theoretical models suggest that under extreme conditions, like near the event horizon of a black hole or in the early moments of the universe, quantum effects might dominate even at stellar scales. How could such a star behave? Picture this. From one moment to the next, the star's position, brightness, or even its gravitational pull could appear to shift unpredictably. Telescopes might detect it in one location, only for it to blink elsewhere without traversing the space in between. Its light could arrive at Earth in overlapping wavelengths, as if multiple versions of the star were emitting photons simultaneously. Even its own nuclear fusion processes might flicker in and out of coherence, as protons in its core tunnel through energy barriers in ways that defy classical physics. Detecting a quantum star would require rethinking astronomy itself. Traditional observation relies on consistent, predictable signals, but this star would be anything but. Scientists might hunt for anomalies like stars that appear to teleport in high-resolution surveys or objects whose spectra show impossible contradictions, signatures of multiple quantum states at once. Gravitational wave detectors could play a role too. If a star in superposition collapsed into a black hole, the resulting waves might carry echoes of its quantum past, like ripples from a stone thrown into a pond by an invisible hand. The most mind-bending possibility, this star might not be a fluke, it could be a window into a deeper truth about the universe. If superposition can persist at stellar scales, it hints that reality itself might be far more fluid than we've ever imagined. Perhaps the cosmos is filled with objects hovering between states, their furies undecided until some cosmic observer, whether a telescope or the fabric of space-time itself, forces a choice. It's a reminder that the universe's greatest mysteries aren't always about what's hidden in darkness, but what exists in the shimmering, uncertain space between is and isn't. At the dawn of time, before galaxies had shape and before planets could form, the very first stars ignited in a universe so alien it would be unrecognizable today. These weren't just early stars, they were cosmic pioneers, forged from nothing but primordial hydrogen and helium in the aftermath of the Big Bang. Astronomers call them population 3 stars, and they were unlike anything that exists now. Towering hundreds of times more massive than our Sun, they burned at temperatures so extreme their light was ultraviolet fury, their lifetimes measured in mere millions of years before erupting in titanic supernova. Yet despite their brilliance, these trailblazers are now lost to us, vanished without a trace, their light stretched into oblivion by the expanding universe. The reason we'll never see them lies in the physics of cosmic evolution. Population 3 stars formed when the universe was less than 100 million years old, a time so distant that the light they emitted has been redshifted far beyond the visible spectrum. Their wavelengths, once bright and piercing, have been stretched by the expansion of space over billions of years into faint infrared whispers, if they haven't faded entirely. Even our most advanced telescopes, like the James Webb Space Telescope, can't detect individual population 3 stars directly, only the faintest hints of their collective glow in the deepest infrared surveys of the early universe. It's like trying to hear the echo of a shout from the other side of the ocean, long after the sound has dissipated into the wind. But if we can't see them, how do we know they existed? The answer is written in the elements they left behind. Population 3 stars were the universe's first alchemists, fusing hydrogen and helium into heavier elements like carbon, oxygen, and iron in their cores, ingredients that didn't exist before them. When they exploded, they seeded the cosmos with these materials, which became the building blocks for future stars, planets, and even life. By studying the oldest stars in our galaxy metal poor relics from just a few generations after population 3, we can reverse engineer the composition of those first stars, like detectives analyzing ashes to reconstruct a long-extinguished fire. The most tantalizing clue comes from distant quasars, whose light passes through ancient gas clouds untouched by later stellar generations. Spectroscopic analysis reveals these clouds contain almost no heavy elements, a smoking gun for a time before population 3 stars had polluted the universe with their ashes. Even more telling are anomalies in the cosmic microwave background, the afterglow of the Big Bang, where subtle temperature fluctuations might encode the gravitational echoes of these first stars' formation. What's haunting is realizing these giants might never be more than theoretical ghosts. Unlike black holes or neutron stars, which leave behind detectable remnants, population 3 stars annihilated themselves so completely that not even their corpses remain. Their supernova were so violent they might have destabilized their own compact cores, leaving no black holes behind, just expanding shells of enriched gas. And yet, their legacy is everywhere, in the iron in our blood, the oxygen we breathe, the silicon in Earth's crust. We are, quite literally, the children of stars we'll never see. Their absence forces us to confront the limits of our cosmic vision. For all our technology, some chapters of the universe's story are closed to us forever, accessible only through indirect traces and theoretical models. But in that mystery lies a profound truth: the universe is far grander, far more inventive than what's visible to our eyes. Population 3 stars remind us that discovery isn't always about seeing. Sometimes it's about learning to read the universe's hidden signatures, written in the language of elements, light, and gravity. And somewhere in those fingerprints, the first stars still speak, if we know how to listen. From the ghostly embrace of the phantom binary to the silent fury of the cosmic vampire, these 30 hidden stars reveal a universe far stranger than the night sky suggests. Some vanish behind cosmic veils of dust and gas, their light stolen before it reaches us. Others are erased by their own companions, drowned in X-ray flares or consumed by black holes. A few defy physics itself, like the quantum star, flickering between realities, or the dark energy star, repelling light with the universe's most mysterious force. Each one proves that what we see is just a fraction of what exists, a shimmering surface over an ocean of darkness. Think about this: for every star visible to the naked eye, there could be dozens hidden in ways we're only beginning to understand. Some are ancient relics, like the population 3 giants whose light faded eons ago. Others are prisoners of their own environments, trapped in the heart of nebulae or orbiting black holes at the edge of annihilation. And then there are the runaway stars flung into the void between galaxies, burning in solitude where no telescope will ever find them. The sheer scale of what we can't see is humbling. It's a reminder that the universe doesn't owe us visibility. It hides its wonders in plain sight, waiting for us to ask the right questions. So what's your favorite cosmic phantom? Is it the zombie star clawing back from the dead, or the rogue star exiled to the abyss? Maybe it's the mirror star reflecting the universe's light so perfectly it disappears. Drop your pick in the comments. We'd love to hear which one sparks your curiosity. And if you're hungry for more mysteries lurking beyond the visible, hit subscribe. The cosmos is full of secrets, and we're just getting started.